So I think that should be it at the moment. I don't see any more people. Let me start with some introductions. My name is Antonis Giannopoulos. I'm a professor of applied geophysics and computational electrodynamics at the University of Edinburgh in Scotland. And I've been working on geophysics and numerical simulation of ground penetrating radars for quite some time. gprMax was something that I started very, very long time ago, in 1997. I believe some of you might not have been born even at that time. It's over 25 years that gprMax has been around, but not really in the form that we actually know it or see it today. It was always a code that I developed for free. People could use it for free. Initially, it was not properly open sourced, primarily because I was afraid for other people to see what's inside. But anyway, quite a few good years now, me and one of my PhD students, which is Dr. Greg Warren, who is now an assistant professor at Northumbria University, would develop this code completely and properly open sourced it. And from then, it's been getting a lot stronger and more, gets more used, and more people is involved with it, and is growing steadily to become quite an interesting code for numerical electromagnetics and simulations. In this, we have to add into the mix Dr. Arnia Patsia, who is with us today, and Dr. Iraklis Giannakis, who is a lecturer in the University of Aberdeen. That I don't know if he managed to join us yet, but as far as I know, he's in the other side of the Atlantic, as he's in Texas on a conference for planetary science. So I suspect it's really very early time in the morning there for this meeting. gprMax is a code that actually solves Maxwell's equations using a very well-known technique. It's called finite difference time domain. It's not very difficult to actually understand how it works mathematically if you really inclined and like physics and you want to find out. But obviously the code itself, apart from doing the numerical solution to Maxwell's equations, it takes care of how people design a scene, what kind of stuff you want to be in the model. It has a lot of other stuff in there to make this kind of modeling a lot more useful. The code doesn't have a graphic user's interface. It's something that people design their models as input files with an increased level of sophistication, especially as we are approaching our next release. And we can run on from big supercomputers to laptops to everywhere in any operating system. And other codes, commercial codes that actually do very similar stuff that what gprMax does in extent, or some of them even more, obviously, they cost a lot of money. So a license for commercial codes that do this type of solutions might cost upwards of $50,000 to $20,000 or more per seat per person, and are quite expensive to use. So gprMax fills a void that is quite useful for many researchers, PhD students, practitioners, even companies, especially in the GPR ground radar world. And also it has applications in other areas of computational electromagnetics, which we want to encourage. We want to see people using gprMax for other things and not just simulation ground penetrating radar. So people can simulate in bioelectromagnetics, for example, to see the interference of how a mobile phone might be going to be placed close to a human head, might raise or might not raise the temperature of the human brain, and in other simulation of antennas and many other kind of stuff. So this is our third time participating in the Google Summer of Code, which is really great fun for us, and it's really nice to be able to use some of your own talents to actually develop the code further. And we have put some projects, as you see, in our GitHub site under the GSoC project ideas. And at the moment, these are 8 projects over there. I don't know if people have any questions at that point that they want to raise before maybe I explain the projects kind of one by one. No. Okay, there is no questions are coming up. So yeah, the first project that is there is called multi-GPU model execution. A few good years ago, we had a project with Google themselves. They're interested in gprMax to actually do some simulations, but they wanted to actually execute on GPUs. At the time, we had an OpenMP multi-threaded kernel, so we can run on multi-processing, multi-core machines primarily, and a simple MPI, message passing interface, domain decomposition parallelization approach that actually was doing task farming in essence, but in a more nice way than actually a job share in a big machine. We developed at the time a GPU kernel, so it runs the simulation using CUDA on NVIDIA GPUs. And that's actually, to an extent, revolutionized pretty much what we can do, because the execution speed of the code on GPUs, because of the nature of the underlying numerical method, is really much improved by any multi-core CPU. If you look at our own website, further down on the first page, you possibly still see a graph that we've done about the comparison of various GPUs in terms of performance. And the small little comparison there, you see that is 20 core CPUs. You see that the difference is really massive. Now, GPUs have been increasingly developed primarily, not obviously for running gprMax, but facilitating AI and machine learning and all this from NVIDIA. And one of the key elements of GPUs is that they increase the memory that's available to them. So you have GPUs that have 24 gigabytes of RAM now, or 11, 12, or even more, or 48, some very expensive ones. And gprMax is a code that actually, when works on volume problems, it requires a lot of memory. It can actually use this amount of memory. Then we'll find out that when we can fit them into the GPU memory, it goes really well. The question here is that can we use multiple GPUs, initially primarily on the same box, on the same machine, to actually do harness, for example, their processing power in tandem, or maybe the memory availability that they have. So we can do even bigger challenging models that we can find out and do that. This is not something that has been done. I'm sure there are commercial codes and other ways that it can be done, but it's a very interesting thing for us to see how if this can be achieved, if it can be achieved. We know that this can be achieved, for example, in cluster computing, in the traditional CPU to CPU communication using message passing interface. It's been these ideas and this technology has been around for a while. And actually, we're going to have a research software engineer working to actually do these for CPUs and big, what you call Beowulf clusters, cluster computing. But it will be very interesting to see if we can do something with using multiple GPUs. The second project, are there any questions about that? Anyone who wants to ask something? Nope. Okay. If you at any point, if you want, just raise your hand or open your mic. It's okay. Then the second project is the Google Colab Jupyter Notebook integration. Basically, as I said, the gprMax is a code that doesn't have really a graphic user interface. You don't design your model using primitives on a CAD package or something like that. You have a number of primitives and approaches and to actually write an input file describing your scene that you want to model, describing where your sources are, where your outputs will be, what you want to get out of the model, all these kind of things, and then run it. That, although initially is a little bit scary for the user, when you get used to it, it allows you to script your input model and create very quickly and with less effort, a lot of interesting models, for example, to train machine learning networks, to do all sorts of interesting things. But the visualization that we need to do sometimes, we're trying to use tools like the VTK, ParaView, for example, to visualize data. And increasingly now we try to use Jupyter notebooks, maybe Jupyter Lab, or Google Colab as well. We have run gprMax or Google Colab for training sessions. And really we want to go down that path that we can use notebooks or Colab or this kind as an interface in a way to make modeling and using gprMax a lot more straightforward for the users who don't really or get scared when they see a terminal window in a computing environment. And that actually will help people trying to create more educational activities as well, when you have some explanation, some training, and you can combine a lot of fees of visualization together with running parts of the code and plotting at the same time. So it doesn't mean that you want to create a massive new, very different interface, but actually have an environment to an extent maybe a lot more friendly to use an experiment with what gprMax can do. And that's basically project number 2. And the project 3 is optimization for Apple Silicon CPUs. We use a lot of Apple computing amongst ourselves. Primarily myself, I do that because I started all this work when I was quite young as a PhD student. And this was the time that Linux came out in early 90s. And I used Linux for very long time, for many, many years. And Linux is actually very good because it allows you to develop code that runs on small computers like PCs and x86 computers. And also the same thing that you do translates to the big machines. And that was really great. I mean, I used to install Linux with floppy disks at the time. However, when you get a job anywhere, you have to deal with administration and writing documents and suddenly using Word and things like that. So Apple was a good compromise between Unix style tools a lot at the time and then being able to do other kind of things. However, as Apple now is moving away from the Intel 8086 platform, and which actually makes life a little bit more tricky on computation, we'll find out that using what we call OpenMP, which is a technology that allows you to do multi-threading quite easily, it's becoming more challenging to port gprMax and let it work on Apple computers, especially now the ones that are actually going to use their own ARM-based but M1, M2 silicon for the main processing units. And OpenMP doesn't work on Apple, and there is obviously other approaches to do that. The reason we need to find out how to actually do a lot better in Apple silicon is because part of gprMax, although is developed in Python, are processed using siphon. And for you who never really come across siphon is a package in a way that you can use some primitives and decorations in Python code, if you like, to actually signify the generation of C code that allows to actually be compiled and used as a module, as a library in a Python code. That actually gives you the benefits of two worlds. You have Python, which is extremely versatile in many, many kind of ways. And then you can actually use real C code for the very critical paths of computation when you need performance. Because as we know, Python, even with the tricks that you can do with NumPy and other kind of technologies that are coming out even now, it doesn't compare, obviously, in terms of execution speed with the native C code. So we use this, the best of both worlds in a way. You develop in Python, which is not extremely different from Python. It's just typecasting of what you think the variables might be. But this translation of Cython to C using OpenMP for parallelization, for multi-threading, doesn't work very well on Apple Silicon, and we want to actually try and see if we can do better here. Now, there is project 4. Again, this is performance gains through memory usage and cache access. It's actually it's a project that actually will look on how to optimize even more our processing capability, the speed in a way, doing something more clever with how we use memory or the memory bandwidth that we have, how to improve the cache access or cache mishits if we can. There is a technology like FEDXPU technology that we're looking at. This is a project, I think, that Craig, who sadly is in the middle of the Atlantic as we speak, is going to be run. Now, someone put a question about, can we use some other compiler instead of Cython, example, Numba? We'll look at Numba. To be really honest, yeah, here you go. Is Shankar, you have a question? Is this Sanskar?
Oh yeah, hey, sorry. Dennis, can you hear me? Hello?
No? Okay, all right, I'll continue. Yeah, Numba is something that we're looking around, technologies that are coming out to actually speed up Python code. I wouldn't be negative of if someone tries and see how Numba compares with Cython. I wasn't so sure that Numba will allow you to do multi-core when we looked at it. But then again, obviously, we don't really look at these technologies every day to actually change the whole core of gprMax. A design decision was taking quite some time. At the time, we considered Swig, for example, which I worked and I know for many, many years, Cython, and looked on all the other technologies that were there that allows you to translate to C code and increase the speed of execution, either on the fly or by have compiled beforehand. If Numba and these technologies have moved on and compare quite well with Cython, if someone wants to do a small comparison, say, look, this is where we go, and then we can have more gains and more easily to actually go for platform to platform or less dependency on compilers, because, for example, we have to be using GCC, obviously, because it's open source and it's quite good compiler, but on various platforms like Apple, that's not as necessarily the easiest way to do it. You have to use Homebrew and stuff like this to do it. So we're not against someone considering this as part of increasing or making the execution speed faster or easier and translating from Cython to Numba. But we do use Cython quite a bit, and we have to be careful to see if, first of all, if this kind of technologies will improve or solve a problem than actually just introducing a different one. Yeah, I mean, yeah, so I think all these questions that are there from Zafar as well, we will open to discuss ways that will end up to an improvement, if we like. If we can see that we can change things from Cython back to Python to see other types of optimizations, and then going back to Cython or Numba or other technologies that speed up execution, then that's something that we can discuss. We're not necessarily, I suspect, have to do Cython by default, but in order to be convinced to abandon Cython for something else that actually will solve problems and be equally fast or faster, then we have to see that this is something that can work and see what time scales that might take as a project. One thing you don't want is to be sometime run out of time and be haphazardly somewhere in the middle and have nothing to actually run on. Yes, Sanskar, I could hear you. I see your message, but couldn't hear you. But I don't know if that's a problem with my. Hope it's no problem with my mic. So
let's check again. No, okay, yeah.
Yeah, the OpenMP is not supported in macOS. What was the multi-core thing on macOS? I suppose was OpenCL that came on for quite some time. And OpenCL is obviously we had a Google project with OpenCL, and we have a working solution, maybe not as optimized, but working, I think, on our development branch with using OpenCL, which will allow you to run on GPUs that are not made by NVIDIA. AMD GPUs, Intel GPUs, and also Apple's CPUs used to. But Apple, I think, is moving away from OpenCL as well. And they have their own, I suspect, software or platforms or frameworks that they're developing on their own development. I don't know in detail what will be the solution. I think that you possibly can still use OpenCL in Apple silicon to do that. And that might be a road that we need to evaluate. Sadly, all these projects are a lot more close to what Craig would like to run, who is the lead programmer by a massive margin on gprMax, like the 95% of development is in terms of the code. It's himself and Dr. John Hartley, who's not with us today, who worked a lot on gprMax as well. A lot of us, the others, are looking a little bit more on the features and the theory and how it translate to code or to gprMax. Now, performance gains we discussed. Now, decouple model building and execution, project number 5, is basically it's an investigation of how we can actually split the process of creating models. Creating models, can be as simple as saying, I have a bit of empty space and I have a source here and a receiver here. What happens in between them? That's an extremely trivial, simple thing, not really very useful in a sense. But obviously, model building for us, when we create an Earth model with targets inside, with real antennas and transducers, and a lot of other kind of interesting things on it, it's not a simple problem. And usually this is a serial process. You have to put things into the model, a box there, and a cylinder there, and target there, or whatever. And this is happening with an approach like a canvas painting, like you put things, and then the next things you put in the model space override, if you like, the things that you put before. And this, with combination of these things, you create a more complex scene, if you like, in your model. But this is more a serial process. And sometimes, you believe it, for very complex models, when you have to manipulate a lot of parts of your simulation space, it can be quite time consuming. And we want to see is something that, if we can improve on that, and especially when we do generating of models that they have to alter and they have to run a lot of them. For example, in GPR research, we have a position of an antenna and a receiver, and then you move it along the again and again on your model scene to get new data. And if you do that every time, obviously you have to move them. You create a new model. Will make some speed gains, but not reusing, but reusing some stuff and not recreating from the beginning. But still, that takes process. So the idea is, can if the model and execution phases be more independent and have a process that actually creates the models, are getting ready to go into the solver and run without having to stop solving completely, create the new model, get running, and then do that again and again and again. So the program number 6, I can see a comment here on Yeah, I mean, regarding idea number 2, Srutanik, I think, is asking if to integrate Jupyter Notebook for Colab, is it possible that a separate Python library could be created so that it will be easy to use, just be by importing it, one can use it in notebooks? Yeah, again, in our new development version of gprMax, we have 2 different types of creating input files and running it. One would be just completely as like a Python script that you can call it in a way as part of libraries. The other is that you have a more traditional execution, that you have an input file that is instructions in a kind of language that go into a program that executes. There is the way that can be done more efficiently for us is up for discussion, negotiation with you on what you think is your ideas, and see how it can work, how easy it will be for the final user, how easy it is for people to get on and use that. So I don't think we have any problem discussing anything of that kind. Yeah, I mean, model building. Okay, yeah, exactly. Paul raises that because it's possibly using gprMax. And if you do big models to create them, the models are created only on CPUs as well. The question there is, can we do that utilizing GPU? Can we speed them up or do them not sequentially before the running? And especially for GPU simulation, that can be really quite important. Optimizing GPU performance. We have a lot of see if how we can optimize further GPU performance, what we can do better without. We have seen that we have a lot of good performance on running on GPUs. We have created some of what we'll say possibly efficient kernels in CUDA to actually do that, and we have good support when we develop that. Initially for people who actually knew CUDA quite well and were NVIDIA fellows. But optimizing performance there is always a key, because for us, I think the future will lie on running on GPUs, because makes gprMax very, very efficient, very fast, and allows to tackle problems that before it would have taken a lot of time to compute. So this is the road to actually try to get to do a lot more interesting research, having a tool that runs quite quickly. Is the GPU solver an extension of the CPU solver? Now I don't know what's the right answer to this. If it is, I mean, the GPU solver does the same things that the CPU solver will do. So basically, if you see that the development of the GPU solver will be a translation of the mechanics of the CPU solver, the mathematics being translated into code in the specific for loops on a CPU solver, then these ideas somehow have translated into the way a GPU solver will work. So for example, on a GPU solver, for us, we serialize completely the memory. In a computer, the memory is obviously in a series of places, or in silicon, that's okay. But the way you access it in programming languages, even in C through matrices, is a lot different than you possibly want to access it more efficiently on a GPU. And that creates a little bit of trickery to how you translate what is the CPU kernel into a GPU equivalent kernel. But the GPU solver takes parts of that becoming on CPU. Once everything is pre-settled, is moved into the memory of the GPU, and then it gets executed there. So I wouldn't say that it's an extension to the CPU solver, but it has to follow specific patterns that are in the CPU solver as well. And these patterns sometimes are dictated by the underlying mathematical method, not necessarily because we just follow what happens in CPU. There are some things in a numerical technique that have to happen in a specific order. And if you don't do them in that order, then you will fail. So another, where are we? Yes. Improve installation tools. Again, obviously, because we have various parts in gprMax, it is a Python package primarily, but we have the siphon bits that they have to be compiled for the specific platform that's been gprMax will run. So at the moment, we created a Python environment, installing a C compiler that has OpenMP support at GCC most of the time, and building and installing the gprMax. This can be a lengthy and complex procedure. And when someone is inexperienced and it doesn't work with terminals and just wants to do that, then becomes a little bit more daunting exercise. And is what we want to do is actually want to simplify and make the installation a lot more easier. So for the people who actually want to use gprMax, this becomes a little more of a daunting task. For us that we use it a lot, we don't see it as a daunting task as much, but it's a different thing when you have someone who has no really very strong computing background, but is a researcher and wants to actually try and use this tool. We don't really want to convert this person to a computing programmer or by default in order to be able to use the tool. So the easiest it becomes for the user, the better it is, and the more people will help, if you like, on their quest and their research and the things that we need to do. So this is something that we want to investigate, how more simple and easier will be to actually try and improve our installation at the moment. Finally, the last project, but not least, is something that is extremely close to my heart, is basically implementing what you call a Planewaves source. Now, that is something that gprMax used to have when I wrote it very long time in C. It's not a feature that is very common in ground penetrating radar work. We don't really need it as much for GPR, but it's very useful when you want to do general electromagnetic simulation, is that you have a source that mimics a plane wave. Now, a plane wave, I don't know what kind of backgrounds you people have in terms of waves or electrical engineering or not, but a plane wave is a wave that in reality really doesn't exist, but mathematically is very useful. It has infinite extent in terms of its propagation. So it goes in one direction, but in the perpendicular to that direction is infinite. Now, in a finite computational grid, this cannot easily achieve because the edges of your model distort this infinite wave and distort its shape, which is supposed to be like a plane hitting you hitting your target. So there are many techniques to implement this in FTDD, and we all have them. It's nothing secret there. I have developed, again, a trial and test in Matlab when I was for a research visit to Hong Kong a few months ago, and I know that it works and it's quite all right. And we want to bring it back on gprMax as a feature. That is something that can take what kind of created as a proof of concept in Matlab. Here has been written like translating an existing Matlab code to Python. And that was like Craig put that project in after we discussed it, but it's not as simple as just translating. It's not that something which is in Matlab exactly becomes exactly the same in Python and is done. It has to take something that is proven in Matlab that it works and be moved into the bigger Python code in the proper way that we do sources and all these kind of things. We know how to do it, but it needs to be translated into code appropriately to be imported in gprMax. So in terms of the mathematics, the why it works, how it works, this is not going to be your task, because that will be very, very small amount of time to actually be able to do that. And especially if you don't have a background in electromagnetics, not that that is really that difficult, but you have to have something to be able to do that. It is something that will be very, very useful for us. With that, we want to do what you call a near to far field transformation as well, but I don't know if we have it as part of this project, or we can increase that project and include it. But implementing the source is the first step. An extension to that project can be to implement a source that it works when you have also a half space target, not just being a homogeneous space. And that is slightly different. Again, we have the theory, we know how it has to be done, but this is a different task that, depending on the size of the project and if there is time or skills of someone who wants to take it on as that he wants to get involved with it, we can discuss and see if we can bring it on or not. But creating a simple Planewave source is something that a lot of people will find useful when you do different studies with gprMax. So it's something that we'll really like to see coming back. The idea was that I will implement this, but sadly, at my stage and the other stuff that life asks me to do is the time for me to actually spend to implement it is not really feasible. So if we find someone that wants to actually do that, that will be really helpful for us. I see another question here. Idea 2 on adding on what Sutanik asks. So can idea 2 be diluted down to creating a library of gprMax and adding the functionality of the ability to display using VDK in terms of the integration of with the Jupyter notebook? I mean, I don't really see why this wouldn't be. I mean, we have run gprMax on cloud services like Google Colab and on Jupyter locally installed or with other services that we have here. And these are, I mean, it is more involved how you install it and how you go about it and what you think that you have to actually initialize in order to be able to start using it. So if something has been created that encapsulates gprMax, that to be able to install it and use it in Jupyter very quickly, that should be okay. Now, the VDK thing we have tried, and Rania, who is here, actually, she can make some good projects and try to actually use the VDK in a Jupyter environment, but it doesn't really, we haven't really succeeded yet. There are various ways to do that. One way is to actually to use ParaView on a server or a compute server and get remote execution and get the results. That requires to have ParaView somewhere and be able to connect through your Jupyter notebook into that. That might be an avenue for some installations. The nicest thing will be to have some kind of visualization that can go into the Jupyter notebook to do that. Another way to see that is that maybe we can have some visualization in Jupyter notebooks or Colab, and that I'm talking over my head in a way that might be don't have to use VDK. If we can do what we want and be able to visualize data nicely in these environments and not necessarily have to use VDK, then that might not be a problem either. I mean, we do export our data in HDF5, and we create VTK, VTP, VTI files automatically to be used with ParaView for geometry views and stuff. But that doesn't mean that if we find something more efficient that it can be used for visualization equally well, like what ParaView can produce or similar, then we're not wedded to ParaView in that kind of way. We just find it an extremely useful tool and allow us to do complex visualizations, which is good for free as is open source. But it doesn't mean that other solutions might not be appropriate. Yes, I can see Paul's question. Yeah, actually, yeah, doing simulations with Planewaves or for having your antennas above ground, you know, like simulating a horn antenna when you're a bit far off, it's all kind of okay. This Planewave source is not going to do that exactly, because that is a Planewave source that assumes that your target is embedded in a homogeneous medium, and a half space is not such like this. So that makes it a little more complicated. The simple Planewave source for being in a homogeneous medium is very easy to do, and doing what you described is doable. The theory, the mathematics are there, but not necessarily equally as straightforward. For some simple cases, when you have only one layer, it might be a lot easier. If you have to have your wave perpendicular to the target, it's not that difficult. If you have to have angles, that becomes a little more tricky. And the more you generalize the case of having a half space with layers in it, it becomes a little more demanding. The mathematics and the procedures of how to do it, they're not secret. They're not very popular. You know, not everybody has developed them, but we know how to do it. But it might be a little bit more involved. So we wanted to start for something simpler that is achievable and we know clearly how it's done, than actually putting a project that can be a bit too taxing if the person has no underlying understanding of the electromagnetics, which we don't assume that most of you people would do, because your interest is primarily in programming and coding and not necessarily in the EM simulation. Yes, the source is not existing. The Planewaves source that, the theory and the simple Matlab implementation doesn't exist on the GPU. Initially, it would be easy to translate it directly to the CPU, and we would like to actually have it on the GPU. And as we have other sources on the GPU, it should be possible to do it. It should be possible to be introduced on the GPU as well. Yeah, the thing with the Pi Vista and server client communication, I mean, I think that first of all, one of the things that we might want to do, if the people who are interested in this project, it's very easy to, and it will be very helpful if you want to apply for that, to do a bit of research and see what is doable, what's not doable, and where some gotchas might be. I mean, we have looked at these things before, and we've looked at client server things. I mean, for us, if we have something that doesn't depend on having a ParaView installation somewhere on a big server, it might be better. And there are some libraries there that you can actually don't really need to install ParaView or have it somewhere to communicate with it. Saying that, if there is an easy way to integrate that and demonstrate a client server thing with ParaView running somewhere that you're accessing, that can be another useful angle to take for situations where people have ParaView on a server and they just want to hook up to it and do visualizations because they have it running all the time and use Jupyter to actually do that. That's interesting as well. Not the same thing. Combining the two possibly will be perfect, but might be a bigger project and possibly require skills that some people might have or might not. But that's something we can discuss. And if you want to look into this, what I'll advise you to do is actually do a little bit of research, see what's about, what can be done, play a little bit with that, and that would be quite an interesting thing to see. I think the mentor for Project 4 and Project 6, I suspect, most likely will be Dr. Greg Warren, who is actually the lead developer and looking after the code, most of that. But let me say that on the outset, because we are a very small organization in terms of how we work with gprMax. What we tended to do of the previous Google Summer of Codes that we actually work with, we all 4 or 5 of us who have weekly meetings with all the interns together, and we discuss issues, projects, and problems, and everybody chips in depending on the expertise or what the problem is. Obviously, some people who know more than others on the specific direction, specific projects, and what you do, you work one-to-one with your mentor on this kind of thing. So if someone takes the Planewave and he has a question about, what does these variables go and why we're doing this and how the mechanics of this is work, then obviously I will be the person to be able to answer that, and we'll do that in one-to-one situation, either with a meeting or emails or Slack or whatever medium we'll find. But in terms of the code and the development and how it goes in and when does it go, we will discuss that with the other mentors as well, because we're all looking after the code. And actually some of us, like Craig, who will know the ins and outs of the code and the way that is currently designed for the last release a lot more than some of us do. And because we're small enough, it's actually quite nice to be able all to work together and have a good chat on this thing. And it's quite easy these days with the technologies that we have to, wherever we are in the world, even if we're away in the summer, somewhere warmer than Scotland that I'm at the moment, you can do that. So it's quite easy. Project 2. I think for Project 2, most likely will be Rania. who has done a lot of work on Jupyter. I mean, she uses Jupyter a lot and integration with that, and Dr. Patsia she has just done a lot of work with machine learning and using Jupyter notebooks and this. So she is the one that I think knows a lot more about anybody else on that topic. Yes, I think at the moment, I mean, we have Git. There are so many tools these days, and it's really hard to keep up with some of them. I mean, recently we start using Slack a lot more for some other kind of work, and we do have Gitter, and Gitter can be the place to host this thing. But we are in discussion with the other mentors and Craig and Iraklis and Anya to see if maybe makes sense to move from Gitter to Slack. But there's something that we obviously make announcements and let everybody know clearly. At the moment, as Gitter is there, you can use that as it is. But obviously, if you have questions as well directly for someone, you can actually email us as well. That's not really a problem either. I think all these things are a lot better for you. For older folk like myself, I try to keep up with all this, but I don't know how good job I'm doing. So any other questions or anyone who wants to say something?
Hello, am I audible? Hello. Okay.
Yeah, that's a good question, Alex. I think what I'll tell you what I do with my thesis students on undergraduate projects that actually are supervised, but then sadly I have to assess as well and mark. I think what will be quite happy to actually ask any questions that to answer questions that you might have about structure, about directions, about things. So is it that feasible? How we see that or whatever. I wouldn't really like to actually have to review in a way to provide feedback and corrections, if I can say that word, to a proposal that is going to be submitted for me to assess afterwards. In a way, yeah, because I mean, one of these things is you want to see how people actually work, think independently on their own accord and stuff. However, saying that is really not a great thing to actually have people working on blind. I mean, I don't find that is useful. So as you develop a proposal, if you go down some direction and say, I'm thinking of that, is it something that, is it right, is it wrong, is it this, what about this idea, or is it something that you don't really want to go down that route because you might have gone and it doesn't work or whatever. Any questions that you might have on this is just fire them up to us and we'll try to answer them as best we can. Yeah, so we don't really want to be in a silence mode. You just go develop something and then we'll see what we like or not. But equally, it doesn't really make sense to actually get pre-submitted proposals or to review correct in a way and say, put them back in and then I'll tell you if I liked it again or not. I mean, it's a little bit tricky. I don't know. I mean, I think we need to discuss with the other mentors as well to see if that is the best approach. And we'll make an announcement to everybody on this. Yeah, for Project 8, the Matlab code is not publicly available. It's something that I've wrote to develop. I didn't develop the idea. I used the research papers and people, the work that they've done to actually see how they work, how they can work in gprMax. And I use Matlab because I'm old and because I've used Matlab for a long time, and it's easier for me instead of doing it directly in Python to actually see if the idea works and I can play with it. So this code, once we start, could be there. It's not publicly available because it's not really, It has no single comment in it. Yeah, it's not a proper code. It's just a hack that I do to say, which I know what it's doing to actually see the results. So that demonstrates that the approach that is from a paper, which we can actually point you to read it if you like, when it's translated to code, it works. It's not that difficult. And what the people published as an idea of how to implement this is actually okay, and it works quite well. This idea is available already on the paper that these people published. It's called a discrete plane wave source. And then it is in books for finite difference time domain. He made it recently to one revision of them. So I'll have a look at the code and see if I can put it somewhere so people can see. But I don't think that, I don't want people to be scared because there's no comments and stuff in it. There's nothing difficult in a way. And obviously, the more physics you understand of what it's doing, the easiest it is, but you don't have to. We'll try to make all these projects that we're trying to have here, projects about the code and how we develop it further. And any physics that might have to come in, or explanations why something happens that way because of what gprMax does as a numerical simulation code, this is something that we will bring in. So I wouldn't expect someone to have a PhD in electromagnetics or a master's or even understanding electromagnetic theory well, because that is high level undergraduate electrical engineering stuff, or even graduate and further. So that would be a bit unfair, and we don't really need to do that. So there will be no question of the kind, this is what happens in theory, how we translate that in practice, and you have to understand how Maxwell's equation works and all these things that are happening with it. Yeah, it's a technical thing. This is what happens in this procedural thing, how we translate it to a good code that actually implements it. That's basically what it's going to be. And I will be there for specifically for that, to be answering the questions on why that has to be there and what does it do, if you need to know, if you don't want to, if you don't understand something on that matter. I think I'll try to clear up the Matlab code and put that on, but I wouldn't really. It's not as straightforward as just translating what is in Matlab in Python. I could do it even myself, this, I suppose. It's like taking the idea that is shown to work on a Matlab script and placing it in a bigger code like gprMax, where all the other sources go, which is a little bit more sophisticated than a simple Matlab script. That's kind of the gist of it. Okay, yeah, the link. Sadly, let me see if I find the paper and I'll put it in here. I don't know if I'm allowed to do that, but I'll do it anyway. Let him give me 3 seconds. Again, please don't be put off of the paper. The implementation works and is being done. But if you want to have a look at it, why not? I don't know that most of you wouldn't really have access to IEEE. So if I actually get the paper that I have it here, let me see, Planewaves here. Yes, that's the one. So if can I just drag this thing in here? Oh, okay, I can do that. So I uploaded a PDF, and what is this? Oh, no, this is an open source thing about the gprMax paper. Okay, yeah, no, that's easy to see. The one that is there, the one that underlines the theory of the simple plane wave paper source is the PDF that I uploaded. This is from IEEE transactional tensor propagation, I think, the paper. And most of you, I don't know, some of you, depending on where you are, you possibly have access to it. If you're in universities, you might not do, but anyway, here it is. I hope that's okay. And this is what underlines the theory of how we create the Planewave source. But what you see in that paper, it exists in a Matlab script. And actually, although it might be a little bit scary when you read these things if you have no background, the implementation of it is not really that tragic. Actually, one thing that we do in only numerical techniques, at the end of the day, we add and subtract numbers and multiply them. And sometimes we divide them, but we try to avoid it so we don't divide by 0. That's basically what numerical computation is all about, yeah, at the end. It looks funny when you write it with mathematics and things, but there is not much more into it. The key thing is which numbers you multiply and divide. That's a different thing. But at the end, there is a code that does some things like that. So it shouldn't really be too scared about it. So don't get afraid by what you see on this one. We know how it works. It does work. And there is a code that I've done on it that is actually runs and does it with some loops and stuff like this. So it's not really something that you have to translate from that to code. I mean, in that case, I'll hold your hand quite close, so that will be no problem. Yeah, okay. It's no, there's you know, it is really once you understand how it works, it's not really extremely difficult thing to do. In this paper, basically the clever idea of these people, what they had is that they project the 3D grid in one dimension. This can be done only if you have a plane wave, which actually is one-dimensional. So this thing doesn't work for anything else, but that's why you want it. And what you do when you do this, you mimic the computational inefficiencies of a 3D grid exactly in 1D grid. The problem with implementing these waves is that they cannot be perfect, and they have what you call leakage effects. They create artifacts. That this technique actually is a technique that doesn't have these artifacts. It's really quite matching perfectly the introduction of a plane wave inside this 3D cube that gprMax is. And there is some interesting way why that works. Whoever wants to do and gets to do this project, we can have a discussion on the nuances and the reasons and all these things if you're interested. But otherwise, it's just a simple kind of implementation of these ideas into code, and we know that work. I've done that to prove that it does work, and obviously the people who publish the paper have done that, because otherwise they wouldn't publish it. So it definitely works, and it's okay. So it's something that is not as difficult as this paper might seem to be for someone who's not really initiated to that. So are there any other questions or anything else that you want me to discuss? No, that's quite okay then. So thank you very much for turning up. I will, if you have any more questions or things that you want to ask for any reason, procedural or not, or extensions to a project or different approaches and stuff, we're quite open. I mean, our aim is to try to get more good things for gprMax out of this to help the community that is using it. I think that, I don't know if I mentioned at the very beginning, all the development will happen on the development branch. We have been working on changing gprMax quite drastically. So we're getting out version 4 in a way, and it's almost there, and it's everything on the development branch. So what we're going to boot and all the code that we'll work with is going to be on the development branch and not on the main branch that you see there that most people are using at the moment, which is what is been released. So the development branch is there on the site, and this is the way we are going to go as we integrate new other things that exist already, and new features that came in from other Google Summer of Code projects and from the work of other people on gprMax as researchers. Yeah, so that's basically the place to look at. Okay, excellent. So thank you very much, guys, and have a great day, evening, or afternoon, or wherever you are. And take care and have a good weekend. Yeah, all the best. Good luck. Yes, email info. Yes.